Calculation of electric field and potential due to a dipole. Let's first calculate the potential. Consider AB is an electric dipole. P is a point at a distance r which makes angle theta with the dipole moment. Here it is shown dipole. AB is a dipole. Negative charge is at minus q and positive charge plus q is at B. And we have to calculate at a point which makes angle theta with its middle point, axis passing through its middle point. The dipole moment. Now r1 equal to AP. If this distance is r1 and this distance is r2, so now r1 equals to AP equivalent to m into p. So PO plus OM equals to R plus L cos theta. If this is L, then it will be L cos theta. Again, if this is L, then this will be L cos theta. And R2 will be PB. R2 will be PB equivalent to PN equal to PO minus ON. PO minus ON equals to R minus L cos theta. And dipole moment is in this direction. So potential at P due to dipole, potential at P due to negative charge plus potential at P due to positive charge. Hence Vp equals to, that is potential at P, V minus plus V plus, potential due to negative charge plus the potential due to positive charge equals to 1 by 4 pi epsilon naught minus of q by r1 plus 1 by 4 pi epsilon naught plus q by r2, or equals to q by 4 pi epsilon naught under bracket 1 by r2 minus 1 by r1. Now putting the value for r2 and r1, q by 4 pi epsilon naught 1 by r minus l cos theta minus of 1 by r plus l cos theta. So equals to q by 4 pi epsilon naught under bracket r plus l cos theta minus of r minus l cos theta divided by r square minus l square cos square theta, or q by 4 pi epsilon naught, this value will be 2l cos theta by r square minus l square into cos square theta. Now as r is very greater than l cos theta, so we can write r square minus l square cos square theta equivalent to r square. Hence potential at P Vp will be equals to q into 2l cos theta by 4 pi epsilon naught into r square. Now q into 2l is P, so P cos theta by 4 pi epsilon naught r square. So we have Vp equals to, that is potential at P 1 by 4 pi epsilon naught P cos theta by r square, or 1 by 4 pi epsilon naught P dot r vector by rq. This is in the vector form P, because this also represent a scalar. Now case 1, when theta equal to 0 degree, called in on position, so Vp will be 1 by 4 pi epsilon naught P by r square. This is the situation for in on position, that is it is along the line. A point is on the along the line of dipole or along the direction of dipole. Then this will be formula for potential at a distance r. And case 2, when theta equal to 90 degree, called broadside on position. So Vp equal to 0, that is since cos 90 equal to 0, so in this case potential at this point will be 0. Now to electric field, to calculate electric field, we see the here it is a dipole minus q and plus q charge, its direction is in this direction. And if we see this direction shows the direction of increasing theta cap, and this direction is direction of increasing r or r cap, that is radial direction, and this is theta direction. Here we, at this point there will be electric field in this direction, one in the radial direction, one in the theta direction. So and its resultant will be in this direction. So we can calculate EP vector, that is net electric field at point P, ER vector plus E theta vector. Now we know that ER is minus del V by del R into R cap, plus E theta is given minus 1 by R del Vp by del theta into theta cap, or equals to minus del Vp by del R into R cap minus 1 by R del Vp by del theta into theta cap, where R cap and theta cap is the unit vector along increasing R and theta respectively. Now del Vp by del R, P cos theta by 4 pi epsilon naught del by del R 1 by R square. We have calculated the value of Pp, which here have been placed. So P cos theta by 4 pi epsilon naught, and del by del R, it is differentiation will be minus 2 by R cube, and del Vp by del theta, P by 4 pi epsilon naught R square del cos theta by del theta, and in differentiation of cos theta is minus sin theta. So P by 4 pi epsilon naught R square minus of sin theta. Hence, net electric field at point P will be EPV vector equal to 2 into P cos theta by 4 pi epsilon naught R Q into R cap, plus P cos theta by 4 pi epsilon naught R Q into theta cap, here 1 by R will be multiplied to R, so here it is RQ theta cap. Now tan alpha, that is angle made by resultant vector with ER vector. So E theta by ER equal to P sin theta by 4 pi epsilon naught RQ by 2P cos theta by 4 pi epsilon naught RQ, or 1 by 2 tan theta, or tan alpha equals to 1 by 2 tan theta. Alpha is the angle made by EP vector with radius vector. Now magnitude of EP will be equal to mode of EP under root 2P cos theta by 4 pi epsilon naught RQ to the whole square, plus PE sin theta by 4 pi epsilon naught RQ to the whole square. So taking PE by 4 pi epsilon naught RQ common, PE by 4 pi epsilon naught RQ common, under root 4 cos square theta plus sin square theta, or equals to P by 4 pi epsilon naught RQ under root, this will be 3 cos square theta plus cos square theta plus sin square, this will be 1. So we have magnitude of EP equals to P by 4 pi epsilon naught RQ under root 3 cos square theta plus 1. Now case 1, when theta equals to 0, that is in on position, so EP will be equal to the EP equals to 2P by 4 pi epsilon naught RQ, and this is the maximum value of electric field due to dipole at a distance R. And case 2, when theta equal to 90 degree broad on position, we have electric field EP equal to P by 4 pi epsilon naught into RQ, and this value is minimum. So field due to dipole is minimum in the broad on position and maximum in the end on position. Now potential energy of a dipole placed in uniform external electric field. Here a dipole is placed in the electric field, and a dipole is displaced by a theta, initially theta and then again displaced by d theta, and E vector and P vector direction is shown. When an electric dipole is placed in an electric field E vector, a torque tau P cross E acts on it. If we rotate the dipole through a small angle d theta, the work done by the torque is dw equals to tau into d theta, or dw equals to minus of P sin theta into d theta. The work is negative as the rotation d theta is opposite to the torque. The change in electrical potential energy of the dipole is therefore du equals to minus dw, or P sin theta d theta. Now if Now at angle theta equal to 90 degree, the electrical potential energy of dipole may be assumed to be zero as net work done by the electrical forces in bringing the dipole from T to this position will be zero. This is the case where potential energy is zero. So integrating du from 90 to theta, we have 90 to theta du equal to 90 to theta Pe into E sin theta d theta, or equals to u theta minus u 90, or P into minus of cos theta 90 to 0. Hence u theta equal to minus of Pe cos theta, or minus of Pe vector dot E vector, because u 90 equal to 0 and u 90 cos 90 equal to 0. If the dipole is rotated from theta 1 to theta 2, then work done by external force is du theta 1 to theta 2, del W external equals to u theta 2 minus u theta 1, or equals to minus of Pe cos theta 2 minus of minus Pe cos theta 1, and del W external equal to P into E under bracket cos theta 1 minus cos theta 2. Hence del W electrical equal to minus of del W external equals to P into cos theta 2 minus cos theta 2 theta 1. This is the expression for work done by a dipole in rotating from theta 1 to theta 2. Next, equilibrium of a dipole. Here it is shown electric field in the electric dipole's direction and electric field direction is same. In this case, theta is 0. Now u will be minus P into E cos theta, or minus P into cos 0, or minus of P into E minimum. So potential energy here is minimum, and F net is 0, also tau net is 0. So in this case, in equilibrium position, potential energy of dipole is minimum, and force is net force on the dipole is 0, and net torque on the dipole is 0. Now in this case, a restoring torque acts on the dipole. When displaced from mean position, a restoring torque acts on the dipole. Now a stable equilibrium. When an electric dipole is placed in an uniform electric field, net force on it is 0 for any position of the dipole in the electric field, but torque acting on it is 0 only at theta equal to 0 degree and 180 degree. Thus at these two positions of the dipole, net force or net torque on it is 0, or the dipole is in equilibrium. Of this, theta equal to 0 degree is the stable equilibrium position of the dipole, because potential energy in this position is minimum, that is u equal to minus P into E, and when displaced from this position, a torque starts acting on it, which is restoring in nature and which has tendency to bring the dipole back in its equilibrium position. On the other hand, at theta equal to 180 degree, the potential energy of the dipole is maximum, that is u equal to plus P E into E, and when it is displaced from this position, the torque has a tendency to rotate it in other direction. This torque is not restoring in nature, so this equilibrium is unstable equilibrium position. Here it is shown. In this case, electric field is in this direction and P in this direction. Here theta is 180 degree and u equal to minus P cos 180, or P equal to maximum. F net equal to 0, but tau equal to 0, but it is a unstable equilibrium. Unstable equilibrium, but here E vector, torque opposite in direction. When displaced for mean position, torque acts on opposite direction. A dipole movement 1.6 into 10 to the power minus 6 kilometer is rotated from 60 degree to 120 degree in electric field of magnitude 1.2 into 10 to the power minus 5 volt per meter. What will be the potential energy stored in the dipole or on the dipole? So solution: potential energy stored in the dipole du theta 1 to theta 2 equals to u theta 2 minus u theta 1, or minus of p into e cos theta 2 minus p cos theta 1, or equals to p into e under bracket cos theta 1 minus cos theta 2. Now p is given 1.6 into 10 to the power 6, is 1.2 into 10 to the power 5, and theta 1 is cos 60 and theta 2 is 120. So cos 60 minus cos 120, and solving we get 1.92 into 10 to the power 11 joule. So potential energy stored in the dipole is this value of this value. In above problem, what is the work done by external agent and electrical force? Delta W external theta 1 to theta 2 is equal to du theta 1 theta 2 p into cos theta 1 minus cos theta 2 is equal to 1.92 into 10 to the power 11. But delta W electrical is minus del W external equal to minus 1.92 into 10 to the power minus 11 joule. What is the potential energy of a dipole having each charge of magnitude of 20 microcoulomb and length 20 cm placed in the electric field of magnitude 1.2 into 10 to the power minus 5 Newton per coulomb at an angle of 60 degree? So we have u equals to minus p vector dot e vector, or minus of p into cos theta. So minus of 20 to 10 to the power minus 6 into 20 into 10 to the minus 2 into 1.2 into 10 to the power minus 5 into cos 60. Solving it, we get minus 2.4 into 10 to the power minus 11 joule. Next topic is continuous charge distribution. We have a continuous line and we have to find a continuous charge. We say that linear charge density, we already have defined it in earlier. So we have lambda equal delta q by delta L. So delta q equal lambda dl, and so force at distance r due to this elementary charge will be dE vector equal to 1 by 4 pi epsilon delta q by r dash square into r dash cap, or 1 by 4 pi epsilon naught lambda del by r dash square into r dash cap. So E vector will be sigma all delta E vector, sigma all 1 by 4 pi epsilon naught lambda delta L by r dash square into r dash cap, where r dash is the distance from the point from the elemental charge. Now delta is varying. Very small such that delta L tends to 0, then limit delta L tends to 0 sigma all 1 by 4 pi epsilon naught lambda delta L r dash by r dash square equals to 1 by 4 pi epsilon naught integration. The summation will change into integration lambda dl by r dash square into r dash cap. Similarly, for surface charge density, we consider a surface and we take an element of area delta S in this surface, and whose charge is delta Q. Then the surface charge density is given as sigma to delta by delta S, and we have to calculate the field at a point r dash from the this element. So electric field due to surface element will be delta E vector 1 by 4 pi epsilon naught sigma delta S by r dash square into r dash cap. Hence electric field due to whole surface will be E vector equal to sigma all delta E on 1 by 4 epsilon naught sigma all sigma delta S into r dash square into r dash cap. If the element is very small, that is delta S tends to 0, then we can write E vector equal to 1 by 4 pi epsilon naught integration of sigma ds by r dash square into r dash cap. R dash cap only represent direction, that is it is a unit vector along R dash. Similarly, we can consider volume charge density rho. This is a volumetric body, and we have taken a small volume in this body, whose volume is V, and on this charge is delta Q distributed all over the volume. So we can write rho equal to delta Q by delta V, or delta Q equal to rho into delta V. So electric field due to this volume element will be delta E equal to 1 by 4 pi epsilon rho into delta V by R dash square into R dash cap. So electric field due to whole body will be E vector equal to sigma all delta E vector 1 by 4 pi epsilon naught sigma all rho into delta V by R dash square into R dash cap. Now if delta V is very small, that is delta V tends to 0, then we can write E vector equal to 1 by 4 pi epsilon naught integration of rho dV by R dash square into R dash cap.